Hi class, welcome back. Our next topic is going to be a quantum mechanical model for the vibration and rotation of molecules. But first, a frame of reference for the particle in a box model. This model that we've seen before is useful for describing how wave functions change as energy increases. So here we have a wave function at n equals 1 is different from our wave function at n equals 2, and n equals 2 is higher in energy than n equals 1, and similarly wave function 3 is different from the other and is at the highest energy. So energy and wave functions both change at quantized intervals n. And that's, again, because of standing waves. We can't have a standing wave right here where the points meet the box at the zero energy, so they have to change. But typically speaking, we don't usually draw energy levels with the wave functions. Atomic energy levels are often abbreviated as single lines, here shown to the right, where we have an energy level at n equals 1, an energy level at n equals 2, and an energy level at n equals 3. Since we'll be talking about molecules, let us take a moment to get some background information on molecular energy levels. So let's first take a look at some simple diatomic molecules. So molecular hydrogen is formed with the overlap of a 1s and a 1s orbital to make hydrogen gas, shown here, the Lewis structure, where you can see that we have 2 electrons shared between the 1s orbitals of hydrogen. Now, we can show this bond being formed from atomic orbitals using a molecular orbital diagram, shown here, where we have on the left and on the right, we have atoms of hydrogen. And each one of them has a single electron in a 1s orbital. And on the y-axis, we have increasing energy. So what happens is the 2 orbitals overlap to form a bonding orbital, and those 2 electrons that are each in a hydrogen atom come together to form a more stable, lower energy system. So let's see what's happening here. We have atomic orbitals overlapping. More stable bonding molecular orbitals are then formed. So this is a bonding molecular orbital in the molecule H2. Simultaneously, as a result of that overlap, we also create a less stable antibonding molecular orbital. So that's up here. So the atomic orbitals on the left and right overlap to form molecular orbital here, where there are 2 electrons, and an antibonding molecular orbital where there are no electrons. For a single energy level, that would be called a sigma energy level, and usually formed when you have a single site of overlap when bonding. So that would look like here, like we saw for hydrogen, where we have a 1s and a 1s orbital having 1 site of overlap. The bonding interaction is called a sigma bond. So at the bottom of our diagram, where we have our bonding energy level, we would just call that a sigma energy level. So that is our sigma bond. At the same time, we form a corresponding antibond that is higher in energy. So this higher energy orbital we're going to call a sigma star antibonding molecular orbital. So the whole reason that this antibonding orbital has to exist is because of conservation of energy. If 2 atoms overlap to form something that's more stable, you also have to create something that offsets that stability. And that is this less stable, higher energy molecular orbital. When we have 2 energy levels for a double overlap, we would call that a pi bond. So that would look like something where if you have p orbitals that are aligned with one another and have 2 sites of overlap, that would create a pi bond. And also at a higher energy level, a pi star antibonding. So now let's take a look at what we can use these molecular orbital diagrams for. One thing that we can use them for is to determine the bond order of a molecule. And this is a qualitative analysis of bond strength. So the bond order, which can be derived from a molecular orbital diagram, is equal to 1/2 the number of electrons in bonding orbitals minus 1/2 the number of electrons in antibonding orbitals. So for our example of molecular hydrogen, we have 2 electrons in a bonding orbital and 0 electrons in an antibonding orbital. So using our equation, we have 2 electrons in a sigma bond, we have 0 electrons in our sigma star antibond. So the bond order would be equal to 1/2 of 2 minus 1/2 of 0. And so our bond order would be equal to 1, and that corresponds with a single bond. And that's where we get our single bond in H2. Now, let's move on and talk about something a little bit more advanced, like hydrochloric acid, HCl. So the valence orbitals of hydrochloric acid are the only orbitals that we're going to really care about for our molecular orbital diagram. Hydrogen has an electron configuration of its valence orbitals of being 1s1, that has a single electron in it. Chlorine, 3s2, 3p5, with a total of 7 electrons. So that's just coming from the periodic table, where we have hydrogen is a 1s orbital, and that's all it is. And chlorine is down here in the main group, and here we have our 3p orbital that has 5 electrons in it, and our 3s is full and has 2 electrons. So 3s2, 3p5, for a total of 7 electrons from chlorine. So the number of electrons that we're going to have in our molecular orbital diagram is the sum of hydrogen, 1, and chlorine, 7, to give us 8 electrons total. So let's just keep that in mind. So our molecular orbital diagram for HCl is going to be set up the same way as for hydrogen, but with a few additional details. Our y-axis is still going to be increasing energy. On the left and on the right, we still have atomic orbitals, and these are our valence orbitals. So the 1s atomic orbital for hydrogen is shown on the left, and the 3s and 3p orbitals of chlorine are shown on the right. We have 1 electron from the electron configuration of hydrogen populating this atomic orbital, and we have 7 electrons from chlorine populating the chlorine atomic orbitals in the valence. So, when 3p orbitals overlap with the 1s orbital to form a sigma bond, we get stability. So it turns out, as we'll see in a second, that this is the single site of overlap between the 3pz orbital and the 1s orbital to form a sigma bond. We also get a corresponding antibond. So that is the part that is identical to what happens in hydrogen. More stability in our sigma bond and less stability with our antibody. Additionally, we have 2 other p orbitals that aren't doing anything. So those just get shuffled out to the side and stay at the same energy as they were in the atomic orbital, and these are now considered non-bonding orbitals. Down here, the 3s orbital is too far away from the 1s orbital to overlap, and so it also just moves laterally out to the side at the same energy as it was in its atomic orbital, and there we have another non-bonding orbital. We then add our 8 total electrons into our molecular orbital, 2, 4, 6, 8, and our molecular orbital diagram is now complete. So let's look at what's going on with those non-bonding orbitals, because those are interesting. So non-bonding orbitals are different from bonding and antibonding in that they do not affect the bond order of the molecule. Non-bonding orbitals have 2 possible origins. So one is the symmetry of the atomic orbitals don't match. So that can be explained simply with a cartoon. So if we take our x, y, z coordinate axes and using the right-hand rule, tilt it to the side so the z-axis is going from right to left, we have a nice overlap between the 1s orbital and the 3pz orbital of chlorine. So here is that one site of overlap that's happening, and that's a match. We have the shaded region of the 1s orbital matches perfectly with the shaded region of the 3pz. That matches, that forms our sigma bond. Fantastic. Over here, we can see that we don't really have nice matching. This is our py orbital on chlorine. It matches in shading at the top, but it is a mismatch at the bottom. And that would result in these interactions sort of canceling out one another. So that is not a match. So we would just call that a mismatch, and that ends up being a non-bonding orbital. Similarly, for the the px orbital, we have a match and we have a mismatch, which cancel out one another and give us another non-bonding orbital. So that is the origin of these two non-bonding orbitals. We can also have a non-bonding orbital when the energy gap between atomic orbitals is too great to overlap. So these atomic orbitals on chlorine are shifted down a little bit because chlorine's more electronegative. And so this 3s and this 1s orbital just end up being too far apart in energy to be able to successfully overlap. And so that's where we get our other type of non-bonding orbital. So overall, in our molecular orbital diagram, we have 2, 4, 6 electrons in non-bonding orbitals, and we have 2 electrons in a bonding orbital. And that's summarized over here. 2 electrons in a bonding orbital, that ends up being this sigma bond in the Lewis structure of HCl. And our 6 non-bonding orbitals, or 6 electrons in non-bonding orbitals, can be considered these 6 lone pairs of electrons, also shown in the Lewis structure. Now let's take a more quantum mechanical look at energy levels. So typically what we've seen before is that energy levels show up as these fixed horizontal lines. But that is not as accurate as it needs to be. So what we're going to see now is how energy can change based on internuclear separation, because we are, again, talking about molecules. So now our energy levels are going to appear as wells, not horizontal lines. And that's shown down here. So in this diagram, we have a y-axis that is increasing, and that is energy. And on the x-axis, we have an internuclear distance. So that's the distance between the two atoms. At our lower energy, we have this well, and that is our lower energy level. Slightly higher is our next energy level, which also appears as a well. When drawing this, it's important to keep this energy well slightly to the right of the lower one. So our lower energy level, this would be considered our ground state. Our higher energy level would be considered our first excited state. So let's see what's going on here. In our energy well diagram, what we see is that energy is dependent on nuclear distance. So a typical hydrochloric acid bond length shows up around 1.275 angstroms. So what does this mean? This means that that is the most stable distance between hydrogen and chlorine in this molecule. If hydrogen and chlorine were closer together, it would be less stable and higher in energy. If hydrogen and chlorine were further apart, they would also be less stable and higher in energy. So if we take a look at the ground state, at the bottom of this well, that internuclear distance would correspond with 1.275 angstroms, right here. If we shove the two atoms together, they would be closer than they want to be, and they would become less stable and higher in energy. If we were to pull the atoms apart, then that would also create a less stable system, and that would be over to the right, and energy would increase. Energy is at its lowest, it's most stable, when hydrogen and chlorine are 1.275 angstroms apart. Now, back to how I drew this being slightly to the right. So the excited state well is slightly to the right of the ground state well. Typically, the excited state involves populating antibonding orbitals. And populating antibonding orbitals decreases the bond order of a system. So the result being that the bond is longer, further to the right on the x-axis, and the bond is less stable, higher on the y-axis. So if you imagine going from a ground state to an excited state where we are populating higher energy levels, in hydrochloric acid, that might look like something where you have electrons from non-bonding orbitals being promoted up here into antibonding orbitals. And from our bond order equation, if we start populating antibonding orbitals, we are taking away from the bond order. So we're decreasing the strength of that bond. So if you decrease the strength of the bond, it'll get longer. And that's why the bottom of this well is slightly to the right of the well in the ground state. And it's all higher in energy because it is less stable. So what we've been discussing are electronic ground states and excited states. Electronic energy levels, the horizontal lines. What we're going to do now is introduce additional types of energy levels. So we have electronic, vibrational, rotational, and translational. So let's take a look at what's going on here. Electronic energy are the energy levels that we are all most familiar with. That's typically what we're talking about when we're talking about the ground state and the excited state. These transitions are the highest in energy, which means they have the shortest wavelength, which is why we observe them with UV-Vis spectroscopy. Vibrational energy in molecules has to do with stretching and bending. These transitions are lower in energy and therefore have longer wavelengths, and therefore we observe these with IR spectroscopy, which you may remember from taking a look at organic molecules in organic chemistry. Beyond vibrational energy, we have the even lower energy rotational energy. This is the energy that occurs from molecules rotating and tumbling in space. And that is typically observed with rotational spectroscopy. And even smaller than rotational energy is translational energy. And for us, we are just going to consider that to be very small. Now let's take a quick look at how to compare the relative energies of these transitions. Electronic transitions are our largest. They have the largest gap and are typically what we talk about with the ground state and excited state. Within electronic states, there are vibrational states because these are a lot smaller. And so they occur at smaller energy intervals. So if we were to consider this big gap our delta E, it is getting smaller for vibrational. Rotational is even smaller. And translational is the smallest. A very, very tiny difference in energy.